You can. Okay, good. Okay. Yeah. Hello, friends. Okay. I'm Raghu Prasad. While our good friend Guru Prasad, Dr. Guru Prasad was introducing me, there's a small error. I'm ME from Bangalore City, not from IISc. But of course, first rank is okay. But later I did only PhD in IISc. There's a small correction I want to add. Okay, good then. Very good morning. And I'll be happy today to share a few ideas I have about response spectrum analysis method for quick resistant design. And let me just, recently, hardly a few days back, or even if that's it. I've written a book on structural dynamics in earthquake and blast resistant design. That has been released worldwide about 2-3 days back by the quite a well-known press called CRC Press. There's a group of the Tyler Francis group. So I'll be talking to you about that book, which I have myself written, and I'll be presenting the material from the book as and when it is required. And let me go to the book straight away. If any questions, maybe you can keep them at the end, so that we can talk to you about the questions, and I'll be answering them. Okay. Now, let me go back to the presentation. Yeah, let me come to the first page, or maybe 10th page. Yeah, in my book, I briefly discuss about this, various types of analysis, the static analysis, the dynamic analysis. Both are there in structural dynamics. The static analysis we do when we do what is called as the pseudostatic analysis. Hello? You can't see me? Oh, I see. Okay. Let me see what is it I have to do. Yeah. I present it now. It was there. I presented all that was there. What happened there? Again, that icon is missing. Right side? No, yeah, but it's not seen here on my screen. Okay. Now present now. Okay, is it okay? Your entire screen? Yeah, is it okay? Share. You can see that now? Now? Why? And I'm sharing why you cannot. Okay. Where is okay? Well, there's no okay here. There's a problem with all this, the new technology. I'm not seeing any okay here. Okay. Now? Can you see? Oops. I can see my. You can see? Yeah. Okay. Good. Yeah. Let me come back to the same page. Okay. Okay, good. Now, you can see that now? Okay. There's very general information. I don't spend much time on that. But in types of analysis, we have, even in earthquake resistant design, as you see in IS 1893, various issues like 2002 and 2016 now. You find that there are three methods which are introduced there, which are recommended for earthquake resistant design. The very first one is the pseudostatic method. or equivalent static analysis. Then the next is the response spectrum method. And the third is a rigorous dynamic analysis that called the time history analysis. When do we do all this is the first question, which everyone should be able to know. The very first one is an approximate method, which every structure is capable of. We can all do it very easily. It is same as just our simple static structure analysis. Suppose you are given a frame, a multi-story frame. We know that how to apply the lateral loads at various load levels and analyze it by any of the methods. To start with very approximate methods, we have got the portal method, we have got the cantilever method, we have got the factor method, or we may use many of the early methods, lobe deflection method, or moment distribution method, all that. Well, good. But we don't use them because they are very tedious, they are good enough for 1 or 2 story buildings, but not for very tall buildings. Therefore, we have the computer methods now. There was a well-known matrix analysis in the finite element. And that is already there, incorporated in many of the recent softwares. And the most popular software with which all the structure units use these days is the Etaps. Actually, originally, this Etaps was from, earlier it used to be called as SAP from the California Berkeley group by Professor Wilson and others. That was there even in 70s. We had the SAP 4. Then all that, then finally it became SAP 2000, then non-SAP, there's nodal analysis, all those softwares are there. But now recently, Etaps was also there long back. I think I have come across Etaps somewhere in 90s. That was actually meant only for buildings. Whereas SAP is meant for any structure. It could be any complicated structure. It could be an automobile structure, or could be aircraft structure, or could be a nuclear containment vessel with all its intricacies and complications, or any other structure, and also buildings. But then it became too involved, too much, time consuming and memory consuming, because for buildings, we don't require all those extra features. Therefore, again, the same group started modifying the software only for tall buildings, civil engineering buildings. When you say civil engineering buildings, I want you to again refresh your memory about the assumptions we make in these tall buildings when it comes to earthquake resistant analysis. What are these assumptions? You should not forget these assumptions at all. In fact, after we make these assumptions, we call this as shear building approximation. A shear building approximation of a tall building is very, very obvious and very natural for a reinforced concrete or a steel structure, a tall building, a multi-story building. What are these assumptions? The assumptions are that all the mass of the building, like the live load, the dead load, and whatever loads you impose on the floor, they're all concentrated at the floor levels. So the mass is concentrated at the floor levels. Kindly note this. Then what about the columns? Even the mass of these columns below half the mass above, columns above half the mass below, will be also lumped at the floor level. So finally, all the masses, wherever they are in a building like this, will all be concentrated at the floor levels. And what are these columns doing? Columns are doing only the function of a spring and in resisting the lateral force. You have now come across, you would have come across a spring model system, a spring mass system. It has a spring and a mass. There's a very well-known model which is introduced in all dynamics books. So I got two kinds of analysis. One is a discrete system analysis and the continuous system. In a discrete system, it's called discrete because the degrees of freedom are all discrete. They are at certain points only. So that you can count them. Number of degrees of freedom, 1, 2, 3, 4, like that you say. And where do you have these degrees of freedom or the generalized coordinates? They're always at the mass points. Why is mass given so much importance in dynamics? Because the difference between the dynamic analysis and the static analysis is the inertia force, mx double dot, and it is a force on the right hand side when there is a force vibration problem. Therefore, that mx double dot, which is the inertia force, is the one which comes in dynamic analysis, and therefore mass is given a lot of importance in dynamic analysis, or the inertia force, and therefore we try to identify the degrees of freedom only at the mass points. And therefore we try to concentrate only on the masses of the system and try to concentrate them at certain points, important points by judgment, and then only we identify the coordinates. That's the advantage of a discrete system. So in a discrete system, masses are all discretely identified at certain points, locations, and the degrees of freedom are also located there at those points. So we can count the number of masses, we can count the number of degrees of freedom. And I got the springs accordingly for every mass. There could be one spring, there could be two springs, and all that depending on the requirement. And these springs have the role of that constant k in an equation of motion. Therefore, when I say mx double dot plus k is equal to 0 in a simple frame, a one-story frame, the columns constitute the k, and the mass is at the floor level, and the entire mass is there. And the degree of freedom of x, is identified at the mass point. This is a discrete system, is also called lumped mass system, lumped mass spring system. While continuous system, of course, we'll not talk about it. It's a data dynamic analysis where the degrees of freedom are continuous. Therefore, it is infinite in number, and therefore don't get an ordinary differential equation. You get a partial differential equation because I got two variables. One is a space variable, which we generally call as x. The other is a time variable, which is t. We'll not go into that now. That's a very, very separate topic. Now, let us consider a discrete system. Why I'm talking about that is, in all our assumptions of analyzing tall buildings, is that we assume that all the masses are lumped at the floor levels. Therefore, it becomes a discrete system. And the degrees of freedom are also located or identified at these mass points. Therefore, for a 10-story building, if it is only lateral motion, I'll have only lateral degrees of freedom, x1, x2, x3, x4, x10. So I got 10 degrees of freedom. All these are located at the mass points at the floor levels. Okay, so that is the advantage of having a discrete lumped mass system, which is possible, which is a possible assumption in a building when it takes the name shear building approximation. And columns, whatever mass of the columns, either columns could be assumed to be massless, or mass could be lumped at the floor levels. Take half the column mass to the floor levels, below and above and other. Now, with this assumption and next assumption is that we generally assume that the columns, this is a very important assumption, which is generally true in a tall building, that columns do not undergo any rotations at the floor levels. This is an assumption. Even if there are some rotations there, you can see them after analysis of a software that it will be very small compared to rotations elsewhere. The either is extremely small, negligibly small, or it could be assumed to be 0. So the columns are all rotation less at the floor levels, and the masses are considered at the floor levels, and the degrees of freedom are located at the floor levels. With these assumptions, it was very easy even before the advent of the computers to analyze a tall building for earthquake, because then we assume the entire earthquake force which is there at the base, because an earthquake motion is a base motion, a ground motion is a base motion. So all the shear is there at the base, but then we need to have a method to distribute this base shear to the entire building at various levels. So which are the various levels? Naturally, the floor levels. So we had a method to distribute the base shear divide them into various floor levels and apply them appropriately at the floor levels as a lateral load, either to the right or to the left. Then analyze the building as if it is a building subject to static forces, which are nothing but the base shear themselves at the various floor levels. Analyze it, get all the results, design the building for the appropriate bending moment, shear, and axial force and all. This was a very well-known, very familiar method with all structural engineers who are not so much comfortable with computer analysis and who are very familiar with all this. But now, once the computer came into picture, these assumptions still are valid inside, but we don't have to do any manual analysis, we do computer analysis. But otherwise, you don't want to make shear building approximation, well, fine, go ahead. Then you have the usual finite maintenance method. Assume columns to be having so many elements. Then the slab could be various quadrilateral elements, or a very thick column, a very thick massive slab. You can have solid elements and so on and so forth. And finite element approximations are there, shape functions, all this. Finally, you get so many degrees of freedom to analyze. It won't be 10 degrees of freedom for a 10-story floor. It will become hundreds of degrees of freedom even for a 10-story floor. Because there are so many degrees of freedom within the column itself, within the slab itself, within the various floor beams themselves. So this is okay, but much better accuracy. You get more number of modes. Earlier we were satisfied with only 3 modes. First 3 modes would have been more than enough in those days. But these days you go to 10 modes, 20 modes, 30 modes, depending on the height of the building, the number of members, the complications. But there's a torsion in plan because of the eccentricity in the plan and so on and so forth. And various kinds of all these are possible now. And I will tell you at the end of the lecture, hope we have been able to use these Etaps very intelligently, very wisely, very appropriately for a tall building. Very much in Bangalore, one consultant was a student of mine in IISc, Mr. Prasad. Very often comes and consults me about that. He has been doing a number of buildings in Bangalore, in and around Bangalore, even sometimes outside. They are not less than 30 to 40 stories. Then you get a lot of very interesting problems, basically because of architectural constraints. You can't get away with that because architects are involved very seriously in certain shapes of the building, certain designs of the building, architectural plan, elevation, and that finally ends up as a big problem for the structural engineer because he can't satisfy the IS 1893 if he goes with these assumptions. I mean, he goes with this design of the architect. So either he has to say no to the architect, which is not generally possible because he becomes unpopular. Then he has to find a method to satisfy the IS code 1893 as well as the architect and naturally the user. So this is a challenge now facing all the structural engineers in and around everywhere in the country, outside the country, and so on. You will come to know it now a little later. Now after this, so therefore static analysis is very important because we do the equal static analysis. But then slightly improved static analysis, which is in between the static analysis and the rigorous dynamic analysis, is a response spectrum method. There's a very elegant method. Mostly we all do this. All softwares have advantage. They give this advantage to us, and we do that. And rigorous dynamic analysis is time history method. So you have the equations of motion, as many equations of motion as the degrees of freedom, and analyze them, integrate them by various methods, and either linearly or non-linearly and so on. You should be able to trace the hysteresis loops and so on. All this you can do, and you can feed in the time history of the given earthquake. If you know, you don't know, you can generate that. There are methods to do that. So this is a very, very, very wonderful academic work. Very often useful also in very complicated structures, very tall buildings with a lot of complications or nuclear containment vessels and so on and so forth. We will not go to that today. We just restrict ourselves to response spectrum method. Okay, now we'll go to response spectrum method. Just a minute. I'm going to the particular page. Earthquake resistant design. Are you seeing this? Let me come back to you once. Let me see whether you are able to see this. Oh, okay, good. Now, this is 7th chapter in my book. I call this as earthquake resistant design. Okay. Earthquake resistant design is an important aspect of the structural design. Okay. Is all this there? I don't want to go into all the details of what I have written here. And again, the shear building approximation, you can see that here. Okay, all masses due to self-weight are all this just now. Let me not repeat that. Then I got the response spectrum here. Okay, you can see the response spectrum there. So what is the response spectrum? Response spectrum, I'm sorry, it's a very wonderful concept. Introduced earlier, way back in 1932 by Bayat. Later, the very famous Professor G.W. Hausner of Caltech improved that and tried to apply that for earthquake clustering design. And the very first earthquake for which they got the response spectrum was El Centro 1940. The El Centro is the name of a place in California. Therefore, for generally all earthquakes, they are named after the places where they occur. Like the Taft earthquake, the El Centro earthquake, and Borrega Mountain, these are all the names in America. Then I got the Kyoto earthquake, or I got the earthquakes in India, the Jabalpur earthquake, or the Koyana earthquake, or the Bhuj earthquake, and so on. Therefore, they are named after the places where they occur. Now, this El Centro earthquake, why is it very well known? Why is it so popular amongst all analysts? The reason is it really had a very huge amount of force to shake the buildings and collapse them. Therefore, a lot of disasters took place in those days when El Centro occurred in 1940, particularly north-south component. Earthquakes are generally measured, at certain places by seismographs, and they are measured in the three directions. The two horizontal directions, generally they are, of course, naturally north-south and the east-west. You can call them as X or Y, and the particular ground acceleration. Generally, one of the horizontal ground accelerations will be very large. Like in the case of El Centro, north-south component had 0.33 g as the peak acceleration. So in the time history, when you record an earthquake, it generally lasts for about 30 seconds. But the first few seconds, maybe 3 to 4 seconds, is supposed to be consisting of what is called as a strong motion part. And there, 0.33 g was noted as peak. That is 33% of the weight of a structure was the horizontal force which was shaking the structure. Imagine that. It's very difficult. Now, I just give you a small example now. All this very nature, you can see that the human beings, again, we're all designed very well to be stable on ourselves for vertical loads. Therefore, you can see a weightlifter lifting a weight several times his weight. Like if a fellow is about 80 kg, he can lift a weight about 120 kg or 130 kg and all that with great ease. And these weightlifters are known for that. And that's good. Nobody collapses by lifting a weight of that kind. But very difficult the same weightlifter may be finding it difficult to resist a horizontal force, which is even little about 50% of his own weight. See, for example, you go in a bus, very often in our metro train or buses and all that. You find it very difficult to stand in a stable motion, in a stable way, standing if the bus is moving very fast. That's because you cannot resist the lateral force on the body a little more than 50% of our own body weight. It's very difficult. So we are not designed, our legs, which are nothing but the columns of a building, are not designed to resist this kind of a lateral force. So you would have seen that as we stand in a bus, we try to stand in the direction of the bus only with our feet apart. If you just close your feet apart, because very often the conductor keeps on pushing all of us, we need to give place to others. So we try to stand with our two legs together. Then you find it extremely difficult. There'll be a lot of force on your shoulders holding on to the bar above. That's because the legs are not able to withstand lateral force because of the position. So if the bus becomes a little empty, then we become highly rigid and we keep our legs apart, spread it apart. Then you find it very comfortable. There's less force on your shoulders because it's like a portal frame. the legs are apart, their lateral forces are much better resisted by this couple, C and T couple, through the legs, with the distance between the legs as a lever arm. So this is how the design is of a human being also. So we find it difficult to, in fact, the footballers, the soccer players are very well designed, are trained to resist horizontal forces, because while running so fast, it's very difficult to resist, because when you run very fast on the ground, the friction force is quite less beneath. So they need to be very strong with that little friction force to resist horizontal forces. Whereas the horizontal forces, first of all, he has to kick the football, then he has to resist the motion of the man who is there by his side. He might try to push him, he might try to grab the ball from him. Then he has to withstand these lateral forces. But they are so well trained, their legs are so well trained, they can resist a very high horizontal force. Even if they fall, they know how to fall without injuring themselves. So these are, so this human example I'm telling you, this example of human beings I'm giving you to drive it home, the idea of a lateral force and how difficult it is to withstand a lateral force. So the buildings are also like this, find it difficult to resist a lateral force unless they're properly designed, and the columns essentially have to be designed to resist the lateral force. One frequency or one period of a structure, for a structure, which means a single degree freedom system. So you take a series of single degree freedom systems of different periods, get the maximum value for a given input, maybe a given earthquake. So now when I'm talking about the El Centro earthquake, you feed El Centro earthquake into a single degree freedom system, analyze it, again get the time history of the response, displacement response, velocity response, acceleration response, pick up the mean and pick up the maximum in these responses and plot them. There's only one value. So maximum displacement, you plot against the period of that single equilibrium system, or maximum velocity or the maximum acceleration likewise. Plot them and join all of them for various periods. Then take the next the single equilibrium system, the different periods, and plot all of them. You get a plot. This plot of the maximum responses of a single equilibrium system for a given input for various values of the period is called the response spectrum. This Professor Hausner found it extremely useful for analysis of earthquake. How do you do that? The step number 1 here. Now, let us assume that you already did the static analysis. No need to teach you about that because you're all teachers teaching number of such methods in the classes for various undergraduate levels. Therefore, I need not tell you about the static method. But now, response spectrum method. What do I do? Here again, I do the static method, right? But how do I do? I do a bit of modification here. What is the modification I do? A given structure is there for me. I need to analyze this for an earthquake, given earthquake. Okay. Then I don't worry about the time history of the earthquake. I don't require that. But what I require is, I require the response spectrum of the earthquake, given earthquake, as a plot, as a data. So I assume that it is there for me. That means somehow I've been able to get it. Let me tell you later how it has been obtained. But for the time being, let us assume that I have the response spectrum of a given earthquake. Could be El Centro earthquake, could be Taft earthquake, or could be Bhuj earthquake, or could be Jabalpur, whatever it is. So somebody has done this job for me. So I have the response spectrum with me. Then what will I do? Then I've been given a structure, a portal frame, 10 stories, 15 stories, whatever number of stories. I'm supposed to now analyze this building for a given earthquake whose response spectrum is given to me. And how will I do? Then what I do is, I first do the number 1 step now is to do the free vibration analysis of this 10-story building, or 30-story building, whatever it is given to you. I do the free vibration analysis, and if it, let's say, is a 10-story building, assuming shear building approximation, as I told you already, there will be 10 degrees of freedom because there are 10 masses in a 10-story building, and assume only lateral motion for the time being in only one plane, XY plane. So only in the X direction, the building is supposed to move during earthquake. I'm not considering right away the motion of the building in a plane perpendicular to the um, plane now. That is not in a direction perpendicular to the given plane, and not even torsion, no vertical, nothing is there except simple plane motion of the building due to horizontal motion of the earthquake. Then that means all forces will be only horizontal. Good. Then what I do, how to get these forces? Then I'm doing the free vibration analysis of this. There's a 10-story building, so 10 masses, 10 degrees of freedom. And therefore, when I do the free vibration analysis, I get 10 natural frequencies or corresponding periods. So fundamental natural frequency or the fundamental period. The fundamental natural frequency is the lowest natural frequency, and all of the frequencies 2, 3, 4 up to 10, they become higher and higher, and the highest is 10th frequency, 10th mode frequency. Each one of them is called a mode. I think you are quite familiar with mode. I'll not explain that to you because I think you know it. The first mode frequency is the natural frequency, or the first mode we say, and there is a fundamental frequency. There is the lowest natural frequency. Corresponding period is the fundamental period, or the period of the first mode. That is the largest value of all the other periods, second, third, fourth, and 10th period. Okay. Now, having known this, then what I do, I've been given the response spectrum that is meant for a single degree freedom system. That means I can think of only one period in that plot. Therefore, I pick up the fundamental period of the given frame. Let me say it's about 1 second. I go to the given response spectrum for that given earthquake. Maybe I'm analyzing it for Bhuj earthquake. I go there. Response spectrum is there. I go up, and there's an acceleration response spectrum. It could be displacement velocity, but for the time being, I'm interested in the acceleration response spectrum because that's the one which gives me force. Mass into acceleration is the force. Therefore, I'm giving importance for that. So I go to that response spectrum. Out of the 3 response spectra I got, displacement, velocity, acceleration, I'm now going to the acceleration response spectra or acceleration response spectrum. Spectrum is singular, spectra is plural. Then I choose 1 second there in the plot, go up, find out what the maximum acceleration is. All the values in a response spectrum are the maximum values. You have to remember that very carefully. Is a maximum response plotted over various periods of a single degree freedom system subject to a given input. Here, the input is the Bhuj earthquake, and I get the maximum acceleration for 1 second. That means this structure, the 10-story building which I am now analyzing, in its first mode, when subjected to this Bhuj earthquake, will experience this maximum acceleration. Okay, you keep it aside. Then pick up the second mode period, go to the same response spectrum, go up, find what the value of the maximum acceleration. So like this, you go for all the 10 periods, I got 10 values of the maximum acceleration of this structure in various modes, the fundamental mode and all the modes up to 10th mode. Then, at any point of time, when this 10-story building vibrates during earthquake, it is said, it is known, it is understood, it is experienced, it is tested beyond any doubt that it is a combination of all the modes. Very often I imagine this example of again a human being. Very often I'm fond of giving these examples because when you think of yourself, comparing yourself with the structure, and if that strikes you very well, then you don't forget the fact about the structure. So what is this about ourselves? All of us, human beings, have different kinds of, not modes, but different kinds of moods, you can say. Mode is M-O-D-E, while mood is M-O-O-D. You know that all of us have different moods. We got a very happy mood, we got a very, very happy mood, we got slightly less than that happy mood, we got very sad mood, we got angry mood, we got jealous mood, we got different kinds of, all kinds of revengeful mood, this mood, all kinds of moods are there in every human being. Okay. Now, at any point of time when you react to a person, at any point of time, You react to a person when he comes and talks to you. It's a combination of all this within our mind. But if that man has really done something really very hurting to you, your most angry mood is going to come out then, and you talk only about that. If it's somebody who makes you very, very happy, gives you very good results, gives you a lot of increments, promotions, you talk with only happy mood with him. Like this, at any point of time, when you talk to some general person on the street, is a combination of all that. And you try to design that. If you are a bit worried about the response you are actually having at the person, and if you feel that the fellow is expecting you, like maybe an auto rickshaw driver or a taxi driver, your angry mood comes out there. Or if you go to a shop where the man is giving you a tremendous amount of discount, your happy mood comes there. So it is in our control to project whatever mood you want, because we are made up of all the moods. Like that, the structure is made of all the modes, and it responds to in a particular mode. If that natural frequency of the mode is very close to forcing frequency of that mode, okay, then that mode only becomes predominant. But very often very difficult, because earthquake itself doesn't have any particular frequency. It's a random motion. There's all frequencies within that. Therefore, you can't say what mode is going to be predominant when it responds to an earthquake. Suppose it's a sinusoidal motion is acting on the structure like a wind motion, and that is a lateral force, dynamic force. It has a particular frequency. If that particular frequency is very close to a particular mode, modal frequency, then that mode only becomes predominant. Okay, but in a structure which is subject to earthquake ground motion, no such things happen, and therefore it vibrates with all the modes together. So at any point of time, when you find a structure is vibrating and earthquake is a combination of all the modes. That means we got now 10 maximum acceleration values for various various modes of the structure. That means if the whole structure were to be accelerating, were to be vibrating only in a particular mode, like the fundamental mode, only that maximum acceleration would be there. But it won't happen at any point of time during earthquake, because it is a combination of all the modes. Then how to get the combination? Do you add all these accelerations and say there is a maximum acceleration when it's combined with all the modes? That becomes too conservative. Yeah, you can do that. It's too conservative. It's like, a man is always full of all the modes, means what? He will be just a madman. He can't be that. Some combination. He's a bit angry, but not very angry, but a little happy, not very happy. And okay, all this is a combination of all of us at any point of time with certain weighting factors. Therefore, there are certain weightage factors called the participation factors. You come across this term in any IISc 1893 code or any dynamics book. This participation factor is a weighting factor which tells you how much each mode is contributing in this particular case. That depends on the structural properties and the masses, the stiffness and all. So it varies from structure to structure. Like it varies from person to person. Well, some people are always angry, some people are always happy, some people are always jovial, light-hearted, some people are always sick. The weighting factor for each person is different for different moods. Similarly, the structured properties actually define the various participation factors. And therefore, there's a method by which we multiply each of the modal response, first mode, the fundamental mode, the second, third, fourth, by this weighting factor, and finally get a good sum of all this. And we don't simply add, because we add again becomes very conservative, because at any point of time, it's not that every point will have the same response, because it won't happen that way. Because when you have the combination of various modes, when you add them, it won't happen. Therefore, the best method to get, which is neither simply adding all that, nor very accurate, but in between, is called the root mean square value, or in our IISc 1893 in dynamics books, we call them as SRSS, square root of the sum of the squares. Okay, so that method we adopt, that is to take squares of these various responses, which are already multiplied by the various participation factors, add all of them, take a square root of them, you get a value that is supposed to be very good, most probable value of the response. Could be acceleration, could be velocity, or could be displacement. So this method of adding the various responses of the various modes and making all this SRSS this and all that. There's one more method called CQC. Comes under what's called modal analysis technique. There's also there in my book, which is there in every other dynamics books, and even our IISc 1893 tells you that in all my softwares like Etaps, the Stat Pro, all this, they do this method, like a modal superposition method, or modal summation method, or modal analysis. There's adding all the various modes appropriately by multiplying them by the various participation factors, getting squares, adding them, and taking the square root. Will all come under this. And that's how we all end up with. So this is response spectrum technique in a nutshell. Now, let me go to some details of this. I think maybe I can pause here a little because it may be too difficult for you to have your attention span continuously without asking some questions. So may I stop here, Dr. Guru Prasad, for about 3-4 minutes, 5 minutes for any questions from the audience? Okay, are you able to listen to me? Are you able to hear me properly? Okay. Okay. Now, how much time is there for me? Now it is time. I know. What is the time now? Uh, okay, another maybe 1 hour. Okay, maybe 45 minutes, right? Okay, let me go. Okay, let me show some pictures of the response spectrum. Now, this is design spectra. Are you able to see this spectra? Hello? Yeah. So you can see this, it's a very familiar figure in our course of practice. Okay. And this is response spectra. And of course, the new term called pseudo acceleration. I don't go into all the details now because it's a detailed talk which requires another 1.5 because that will digress from the main idea. But today I want to make you very familiar with the earthquake resistant design using response spectrum. So I essentially concentrate on that. Okay, now these are the spectra generally is of the same shape here. You find a linear portion here. This is first linear portion, and the horizontal portion, and this is curly linear and comes down. So, for example, natural period is here, and now when you go very close to zero here, these periods are very small periods. That means if the period is very small, it means the frequency is very high, the natural frequency. We're talking only about natural period here. The natural frequency. The natural period is very small, the natural frequency is very high. That means it's a very rigid structure. Like in a 2-story building, a 3-story building, a thick, consisting of thick walls, masonry building and all that. And such a building, generally, the accelerations will be more or less the same as that of the ground because it's a very stiff structure. To give an example of that, you consider a pencil or a dot pen. You keep it on a table. Dot pen is a very rigid pencil, rigid an object, rigid object. So when the table slightly shakes, it immediately falls down. Why? Because the acceleration of the response, that is of the pencil, because of the base acceleration of the table, okay, is the same. Or whatever the base acceleration of the table when you shake it is transferred to the pencil as it is. Every point suffers the same acceleration as that of the tabletop, because the pencil there, which is kept on the table, is a very rigid element, not a flexible element. Because it is rigid, you know that. You can't just break it, it's not flexible at all. So every point will suffer the same acceleration as that of the base acceleration, because it's a very rigid one. Supposing you keep a very thin one, a thin wire which can be fixed to some good base, and it is there at the, just always, you have seen that kind of a, we keep that very often on our tables, as an ornamental piece. It will be simply shaking, okay? Like sometimes we keep such things in cars and all that. It will be moving by, it will be oscillating by itself when the car moves. That kind of a flexible spring, okay, or a wire. Then when the table moves with a certain acceleration, the top of that wire doesn't move at all very often. It doesn't move as much as the table moves, because we are on the right extreme here then. Because it's a very flexible object, so its natural period is very high, or the natural frequency is very small. And such a structure has much less than the ground acceleration. Okay? So this is an important property of all structural engineering practice and all structural design and all that. Because we need to see this. So it's not good to design a very rigid building if it has to be very safe. Or you can't make it very flexible because the deflection should be very large. So we try to compromise in between. So that is a good structural engineering practice. Okay. Now, this aspect is now, this property of the structures is actually exploited in abstract clustering design. So this is response spectrum, typical response spectrum, that gives us this idea. Let me go back a little. See, this is called a tripartite plot. It's a very well-known plot. It's a very popular plot. You can see them in all the books. So you have, why it is called tripartite? You got three important parameters shown here. The vertical is the pseudo velocity. Then, of course, the horizontal is the natural vibration period. Of a single degree film system we are talking about. Every time response spectrum is a single degree film system. And there are two inclined lines at 45 degrees. One is the pseudo acceleration, the other is the deformation, relative deformation of the structure. All the three are plotted 1, 2, and 3 against the natural period of the single degree film system. So when you plot that, you get a plot of this kind, okay? And you find it is highly jagged. That is, as the damping is less, this is as the damping improves or increases, we come down like this. So this is for, the lowest one is for very high damping, maybe 5%. As you go up, damping becomes less and less, the damping in the structure, and this may be about 1%. So when the damping is less, you find that the motion is highly jagged, that is very erratic. Well, damping makes it very calm, like, good sedative. You take a good sleeping pill, you become very calm. So like that, damping is like a sleeping pill. Okay, structure becomes very calm. See, but here is not so. It's very restless. So one can draw a response spectrum for various values of damping for a given input. And here you can ask me, what is this? Here is for L center ground motion. Okay. And pseudo velocity, pseudo acceleration, and deformation. What is pseudo? This is a new term I introduced here. When it comes to response spectrum method, and modal method and all that, people introduce this, the researchers introduce this because for certain advantages. So what is this? How to define that? Okay, I'll give an example. Take a single different system. Subject these to time history motion, time history input of any given earthquake. Here in this case, let's say El Centro. Unless that, you got the equation of motion, mx double dot plus cx dot plus kx equal to the right hand side, which is a given earthquake, and fill the time history of the earthquake on the right hand side, integrate the equations of motion, get the response x, get the velocity x dot, and get the acceleration x double dot. Plot algorithm versus time, you get something like the earthquake, only a highly jagged motion over time. Goes up to the time up to which you have integrated the equation of motion. Maybe it could be up to 30 seconds, no problem. Or maybe it could be 5 seconds, no problem. Okay, I got. Now in that, pick up the maximum value of the acceleration in the acceleration versus time. Pick up the maximum value of the velocity in velocity versus time. Pick up the maximum value of displacement in displacement versus time. Plot all of them and get a plot of this kind. This is the plot. But this is plotted in a different type. It's called tripartite plot. It's four-way logarithmic plot. These are logarithmic scales. That's why it looks like that. So there's a method to do that. There's a different thing. I don't talk to you about that method. Finally, you get a plot of this kind. Very easy to see this, make use of that, and for design and all. Now, in this plot, we have introduced a term called pseudo velocity and pseudo acceleration. Why did we do that? Because time is as said, we can pick up the maximum value as said. But that's again too much time consuming. Why should I do all this? What I do is, I do the time history of the displacement. I pick up the maximum displacement. This is another method. I pick up the maximum value of displacement. Then, instead of again going to the time history of the acceleration and the time history of the velocity, what I do is, I pick up the maximum value of displacement or time history of the displacement, multiply that by the natural frequency of the system, omega. So omega x dot becomes the pseudo velocity, maximum value. Omega into x max becomes x dot max, but pseudo. I can give one more symbol. I've given that symbol here. Maybe for the time you can say p. So x dot tp, x dot pm. I'm sorry, x dot pm, which is when I say dot, that is one derivative, that is velocity. When I say x double dot, there are two dots, that is d square x by dt square, that is acceleration. X is displacement. So that means derivative of x is velocity, second derivative of x is acceleration. I think you know that. Now, pick up the maximum value of x, as the maximum displacement from the time history of the displacement, multiply xm by omega, that is omega xm is x dot pm, that is pseudo velocity maximum. That means, because why I call pseudo, I simply multiply that by the natural frequency. I did not go to the time history of the velocity and pick up the maximum value of velocity, which is actually correct value, exact value. But I don't do that. Instead, I just take natural frequency system, multiply that by the maximum value displacement. I call that as also maximum velocity, but is a pseudo velocity, not the exact velocity. Similarly, I take omega square, the square is natural frequency, multiply that by multiply xm by omega square, then I get x double dot m again with a subscript p. So this is pseudo maximum acceleration. Why did we do all this? What is great fun in doing that? The question is, it's very easy to plot, very easy to obtain first of all, and there's nothing, no generality is lost in doing that, because it so happens, the maximum values are when of displacements occurred when velocity is 0. Naturally, the equation of motion then is mx double dot plus kx only. When that is there, if you assume that this x is sinusoidal, it is, let's say, a sin omega t, then when you differentiate that, is a omega cos omega t, and maximum value of it is only a omega. That is, multiply the amplitude of displacement by the natural frequency omega, then you get the maximum value of the velocity in the sinusoidal motion. Similarly, again differentiate, you get a minus a omega square Sin omega t once again. Maximally sin omega t is not there. It is simply minus a omega square. And minus is not required because we're talking about maximum value. So a omega square is a maximum value of the acceleration, where a is the amplitude displacement. This is maximum value displacement. So multiply the maximum displacement by omega, you get maximum velocity. Multiply the maximum displacement by the omega square, you get maximum acceleration. That is true, that is exact if it is sinusoidal. But this is not sinusoidal now in our case. That earthquake is not sinusoidal, it's a random motion. Still, we are doing that here with that assumption, and therefore these values are not same as the exact maximum values. Therefore, they are pseudo values. That has been accepted as a good practice. It's very close to the actual values, but design is very good enough. So we are doing that. So that's why in all books you find a tripartite spectra or a response spectrum. You find this title pseudo velocity or pseudo acceleration, which is obtained by multiplying the maximum displacement of omega or omega square, respectively. This is tripartite spectra. Okay, now, then the next question you would ask me now is, sir, you are telling me El Centro, Taft, and Jabalpur, and Bhuj, and all that. Then what's the response spectrum we should take for our design? I'm now given a design in Bangalore, a tall building in Bangalore to be designed. What earthquake you are going to assume here? Do you expect El Centro earthquake to occur in Bangalore? Or do you expect Bhuj earthquake to occur in Bangalore? Or do you expect something else? Some other earthquake, Jabalpur, Yokohama, anything? Okay? No, I cannot expect, because earthquake itself is so uncertain. Nobody can ever predict earthquake. You never know when it's going to occur. You never know what kind of earthquake is going to occur. When that being so, you can't simply design for any earthquake you want. You are never sure it is safe or unsafe. Or it could be highly uneconomical. Supposing I design all buildings in Bangalore to El Centro earthquake, I'll be called a fool. Because El Centro is such a powerful, strong earthquake. It occurred in 1940. It won't occur again and again. Again, there's one limit state philosophy in earthquake, which you should all know. What does it mean? That when you design for an earthquake, we don't design such that the structure is always elastic for all earthquakes. So in any structure, we got elastic design or the working stress method, or limit state method, that is limit state of collapse method. Very, very well known. Multiply all the loads, live load, dead load, by certain limit factor, load factor. Okay. The safety factors, what we call. And accordingly design. 1.5 is accepted now. Then I design for these limit values, limit loads. That means these are the maximum loads which may occur in the life of the structure. So when such a thing happens, I can now very safely assume maybe at that point of time when the loads are so maximum, so high, the steel perhaps could have been very close to yield value. The concrete could be very close to 0.003 crushing. And therefore, accordingly, I take, all the designs based on this. IS 456 tells you this. Okay. Similarly, in earthquake also we do that. But then, how do we do that? Here, what we do, the earthquakes are now also labeled with an extra adjective called the return period. Okay. The return period of an earthquake is a period over which it again repeats. Okay. Generally, very strong motion earthquakes occur not very often. They occur once in a way. For example, in human beings also we tell you that. For example, people who suffer from COVID now, it's not going to happen every day. It never happened in the last 60 years of the freedom in the country, or 100 years. I think the very first time people able to experience was what's called as the very famous, very infamous influenza, which came from Spain. I believe people who lived in 1920 in Bangalore, they suffered from this, and there were many deaths in Bangalore, all that they say. But that influenza did not continue as influenza throughout. Later it became simple flu. If there's a flu to any person, it doesn't bother. Simply keeps on coughing or sneezing, and after 2-3 days, with some crocin, the other is going to go away. Nobody is really bothered that he's going to die out of flu. But influenza in those days, people were really scared. They would die. Number of people died. There was no because there's what is called as immunity developed and lots of medicines developed and so on and so forth. You are not bothered. But no, suddenly COVID came in between. COVID is like influenza, very scary. People are afraid that they may die out of COVID. Therefore, we're all having lots of precautions around. But after another maybe a couple of years, COVID will become like an ordinary flu. Nobody bothers. Some simple precaution should be enough. Maybe vaccination is there, something else is there. Okay, nobody ever bothers. Okay, like this, anything which happens very ordinarily, like a simple cough, cold, and all that, they can happen quite often. Once in a while, if it rains very heavily, you may get cold. Again, it is not there, like that. Ordinary events can happen very frequently. Extraordinary events happen once in a way. You're extraordinarily happy on the day when you married, therefore only once in a way. So like that, very strong earthquakes, which are highly devastating, can happen only once in a way. That once in a way is highly subjective. Maybe it's 100 years or 200 years, we do not know. I don't think El Centro kind of earthquake did not take it again. It was already there in 1940. Already almost how many years over? 80 years over now. I don't think it has happened again in the same place. Like that. But ordinary earthquakes, maybe Richter's magnitude about 3, 4 and all that. In Bangalore also, one very often experiences some mild shaking. And if you happen to be in Japan, I was there for some time then, very almost now and then there'll be some shaking of a building. So nobody bothers. They say, oh, some mild earthquake, they just laugh and go away. Nobody runs to shelter and all that because they're used to it in Japan and maybe in California. But we're not used to use mild shaking, people get scared. Okay. But even then, mild shaking is no problem. Okay. But it doesn't collapse a building, no loss of life, no loss of property. But very strong motion earthquakes, maybe Richter magnitude 8, 7, 8, and all that, life. That is never. No loss of life is permitted, is acceptable in any design. But some minor shaking, minor collapse here and there, non-structural elements could be there. Then why do you allow that? There's a purpose in doing that. I tell you now. There's what is called a ductility that becomes an important property in structural design, in limit state design. So when you design a structure for an extraordinary event, which happens once in 100 years, an earthquake of magnitude 8, I do design in such a way that structure is still safe, but gets deformed little more than the usual, without any collapse, without any loss of life. But maybe here and there some yielding, some non-structural elements collapse and all that. The ductility of that is also well within limits of the ultimate values, so that the structure still remains deformed quite largely, but not with any collapse. This is what I do for extraordinary events which occur once in 100 years, like ground motions of very high magnitude, Richter magnitude. But for earthquakes of ordinary magnitudes, like 3, 4 and all that, which might occur once in 20 years, 25 years, or maybe 30 years, we do not know. There are separate studies for this. Then for such structures, I do design such that it can remain elastic. Because, okay, there are very small values, it's not going to be very uneconomic. So you can afford to be within elastic limits, then don't bother about ductility and all that, within working stress levels for ordinary events. But for extraordinary events, if you still make them elastic, it's too conservative, it's too uneconomical. Then you do allow some nonlinearity to occur, but without any loss of life. So this is called the limit state philosophy, again, which was actually proposed by Hausner, and is still popular in all IISc courses. You can see that in IIS 1893. Therefore, the concept of ductility came into picture. The concept of capacity spectrum came into picture. So these are all there, mentioned in the IIS 1893, and they're all well incorporated in the Etaps. So you can adopt capacity spectrum method to obtain ductility required and ductility caused due to certain earthquake and all. But I still didn't answer the question. I raised the question yet to answer, but for what earthquake then I should design? So now, given the fact that earthquakes are very uncertain, we do not know what magnitude of the earthquake is going to occur when and how frequently, then the concept of average earthquake came into picture. Again, Hausner was responsible for that. What is an average earthquake? It's very simple. Average, everybody knows. If I got 10 different values, take sum of all of them, divide by 10, you get average. Very simple concept. The same concept will hold good here. So let me, as many earthquakes as possible I can take. That I don't think we can do it in Bangalore, because Bangalore never had such a great many number of earthquakes to have a good average. Maybe 2, 3. Maybe in California, I had number of earthquakes right from after they started instrumenting. Instrumenting means trying to get the acceleration levels of the various earthquakes. That happened somewhere in 1930, 30s in USA itself, such an advanced country. Where do you expect instrumentation in any other country? Japan a little later, okay, or the effects of World War and all that, they too had the enough capacity to have install lot of various accelerometers and get the acceleration levels of the ground. And there are lots of earthquakes recorded. US has a lot of earthquakes recorded. So then they could take the average. So they took the average, and finally, in a spectrum like this, you see here, the tripartite spectra, one could draw what is called as an average spectra. You can see this, something like that. So you can have a line like this, first line, and horizontal line. This is nothing but an average assumption, average shape of a response spectra, a tripartite spectra. That could be an average value. So you take number of earthquakes like this, even more than this, take average values, the mean values, the standard deviation, and get 90 percentile values, 85, 95, 80, all that you know how to get. This is mean plus 3 sigma, mean plus 2 sigma, mean plus sigma, so on and so forth. Get the various average values, that is the probability values, and get diagrams of this kind. These are called average tripartite spectra. Okay, this roughly resembles the same shape as this. Okay. So this kind of average spectra is the one which is going to represent any earthquake which might occur. And such an average spectra is there in our IS 1883. So the spectra which is given in the earthquake course are the average spectra. That is for any earthquake. There is no main name for that. It is neither El Centro, nor Buj, nor Taft, nor Koina. It's an average spectra. So we can use that spectra that can be assumed to be safe, safely, and also wise any place. Whether you design a structure in Chennai or Bombay or very close to Himalayas or Bangalore, same spectra. But again, we classify with a different factor. This is again a multiplying factor depending on the zone. So we got zone 1, zone 2, zone 3, zone 4, and all that. So all that you know, they are there, the zonal classification, and you got the importance factor depending on the importance of the building. So with all that, finally you get the horizontal acceleration coefficient. Simply multiply the total weight by that, you get the base shear, and divide the base shear accordingly with the formula given in the code. You might just do a very simple equal static analysis, or then you do the response spectrum analysis like I said. Every time have a period already known from the free vibration analysis. Go to the average response spectrum or response spectra given in the IS 1893. Get the corresponding acceleration. Keep them in one place. Then like that for all the different periods, maybe 10 periods in a 10 story structure. Then what to do? Then this is for a single different system. Now what I do is multiply the entire variance structure by this acceleration, whatever you get, then you get the base shear. Then this base shear you distribute over the entire building. Similarly, as you did in the equal static analysis. Now do the static analysis. Then you get the various bending moments and shear force and all that. That is for the first mode. Similarly, you do a similar thing for second, third, fourth. Then individually take the SRSS of the various maximum accelerations, various maximum displacements, various maximum velocities and all that, and thereby you design the structure. This is the response spectrum method. Now, let us stop for a while before I show you some examples of actual buildings. So I want you to ask me some questions if there are, and let us have a pause. Just tell me how do you like the presentation till now? Okay, good.
Sir, good morning, sir.
Yeah.
Sir, good morning. I am Rajendra Prasad from PSN Engineering College, Dindukal,
Okay, let me
Tamil
see you.
Nadu.
Let me see you now. Is it possible to see you?
Yes, sir. Yes, sir.
Let me
I can see your screen.
where I'm not getting people here. Ah,
Oh, okay, sir. Okay,
yeah.
sir.
Where are you here? Your name?
Rajendra Prasad from Dindukal, sir, Tamil Nadu.
Oh, okay, okay. Oh, I think
Okay,
last
sir.
month I saw you once. Okay, maybe I'd been to Dindigal.
Yes,
Yeah,
yes.
yeah. Okay. Mm.
Okay, sir. So,
Mm.
at the time of your presentation, earlier you are going to specify SAP can be used for all type of structures.
Little
So,
slow.
in the
Little
time
slow.
history analysis using SAP, so how
Mm.
we are going to change the acceleration parameters? So, if maybe I am going to increase 0 to 1 or maybe 0.1, 0.2 something. So, how I am going to give the input in this?
Change the acceleration parameters. Why? What do you mean changing?
So, because there maybe I am going to get the output for the various acceleration parameters, maybe 0.1, 0.2 or something. So gradually I
Mm.
am going to vary the G value.
No, no. Why you are now doing for a specific response spectrum? So you don't keep varying like that.
Okay, sir.
So you are given a response spectrum now.
Okay,
You
sir.
do the analysis, the free vibration analysis of the structure. Look at the various fundamental periods. From the given response spectrum, pick up all those maximum values and get the maximum base shear for each of the modes. Then do the analysis as if the static analysis, get the various responses, like, in addition to acceleration, velocity, displacement, you also get bending moment, shear force, and all that. Okay, then the SRS values, various values, various response values, and design them accordingly. But you don't change any acceleration now.
Okay, sir. Okay, sir. Okay,
Hmm?
thank you, sir.
Okay. Any other question? How many of you are here? 6 people, is it? 9 people. Hmm. All right. Tell me. Yeah, yeah, it is there. It's a very involved question. It is there. See, uh, in fact, now having asked this question, I want to answer you, Dr. Guru Prasad, that you would have heard of Professor Narayana. He did what is called a microzonation, a big project. He did microzonation of Bangalore. So within zones, you'll find so many small zones. In Bangalore itself, you can have different zones where you get different accelerations. It's possible. Okay. And this microzonation of Delhi he did, and now they are reclassifying the entire country into, again, modifying the zonal values. Okay, and along with him, one Professor Raghu Khan, who did the PhD in our own IISc. Maybe I heard of him. Okay, he worked with Professor Narayana. I know he's a professor in IIT Madras. He has taken a big project funded by, I think, DST. Okay, that is trying to, and he gave a talk recently. According to him, even the present values of the zones, second zone 2, zone 3, and the coefficients are there. They have to be modified. They are terribly wrong according to him. So that needs modification, a thorough modification. That means the code again has to revise. But this is still going on. A lot of debates are going on. A lot of discussions are going on. They have not come to any consensus about that. There's a big codal committee involved in that, including, I think, Professor Narayana, Professor Raghu Khan, and Professor Sudhir Jain of IIT Gandhinagar, and Professor there's one more Murthy, okay, CVR Murthy of IIT Madras. They are discussing about that. Then once they come to a conclusion, I'm sure you find, maybe I don't know, this may, don't quote me, but maybe instead of so many zones I got before, it could be more. We may reclassify the entire country to even more number of zones. Maybe I would do that. So why to only have these 2, 3 and all that? Why not a little more than that? Could be my question. So all this is happening. Therefore, all these definitely are connected with the Richter magnitude. If the Richter magnitude is 8, the zone should have definitely very high acceleration coefficient. Alpha should be very high. If the Richter magnitude is maybe 4, naturally the zonal classification, the zonal acceleration value that alpha could be quite less. But how do you connect that? This is a very big question, which involves a lot of geophysics, okay, and seismology and so on. So I don't have a number right away to tell you, but certainly there is a relationship between the Richter magnitude and this zone. Who? Is he here? I see. No, can you repeat now? You're very fast. Tell me. Yeah, good. Hmm. No, okay. Certainly the question is very obvious. I mean, answer is very obvious. We definitely have a lot of use of probabilistic hazard map in our seismic analysis response. Deterministic does not come anywhere here. Nothing is deterministic here. Everything is probabilistic. Has it been answered? Is it there? Listening to us? Good. Very good. Hmm. No, okay. Before we close, let me show them some buildings in Bangalore, which we did. We'll come back to the presentation. Yeah. Now, let me go. See, various buildings, I told you, one of my former students called Prasad, in Renka Prasad, he has a consultancy office called Prasad Consultants. Uh, he keeps asking me, consulting me very often. He uses, very often Etaps, besides other softwares. Now, for example, two things for example, these are various buildings we have done. Generally, in all the tall buildings, you find what is called as a podium. This is a podium. And you got a tower. You got a tower and a podium. The problem is, this is very common. In all buildings, architects do want this kind of thing. And what happens is, they want a very large space also somewhere in this area, large column free space. Therefore, the idea is to have floating columns on a huge transfer girder. But the IS 1893 strictly prohibits the floating columns. If they are now carrying a large shear, then they should not be there at all. This is very dangerous. They are the one which cause a huge loss of lives. Then these architects do not allow the structural engineers to avoid floating columns. They have floating columns. But then they're all loaded on a transfer girder. Transfer girder would be of the size of something like 1 to 1 meter is too small, maybe 2 to 2.5 meters in depth, very often pre-stressed and all that. Okay, then how do we circumvent these floating columns they want, but we cannot allow floating columns to carry large shear. Then only thing is we can have floating columns because architects want it, but as a section engineer, I can see that shears are not very large on these floating columns. So I design a very good shear wall, okay, at strategic places in a building, such that 100% of the shear is carried by the shear walls. The IS 1893, you can see in the section of the flat slabs that particularly in flat slab structures, you should have shear bars which carry 100% shear, and only 20 to 30% shear is carried by the peripheral columns. So that concept I make use of here, although it is not listed under floating columns by the IS code, that is our innovation. And see that the floating columns do not carry very large shear, they carry very small shear. Then the IS 1893 account to that is okay. So then I have to see that. Then what happens is when I have a very huge shear bar, a thick shear bar to carry all the shear, then the design becomes very different, and still I need to be within limits of economy. Number one. Number two, the podium is here. Okay. The other problem which we generally come across is a participation factors. I told you participation factor is a weighting factor. The IS code says the maximum acceleration mass participation should be not less than 65% of the total mass, the seismic mass. But then, because of the podium, what happens if you take the columns to be fixed at the base level here, at the ground level, up to the roof level, up to the roof of the podium level here, the displacement are generally very small because they are very stiff here. Because the columns are quite strong here, quite stiff, there's a retaining wall here and all that. Therefore, because the eigenvectors are very small up to this level from the ground level, the mass participation up to here is very small, and therefore the total mass participation becomes much less than 65%, which is again not according to the IS 1893. So we found out a method. I suggested a method. What I did was we can have a substructure analysis, assume this has one structure, assume podium as another structure, okay? Then assume the columns to be fixed at the top of the podium, which has to be sufficiently justified. Then we do the analysis, find out the rotations at this level, which are supposed to be quite, which are, according to my assumption, should be quite small compared to rotations at this point, which otherwise we satisfy that by again slightly remodification of the design. And this is a separate structure. Then the two structures themselves independently will have sufficient mass participation factor. So this is another innovation we did in all these tall buildings, in order to satisfy both IS 1893 and the architect. So one more such building is here, and this is the plan. And very often, which we did not talk about that today, is the buildings which are asymmetric in plan. They not only undergo translations in X direction and the Y direction, but also rotation like this in plan. This again makes things very complicated, and the IS code does not want this torsion to be there at all. They are called torsionally irregular structures. They should not be irregular both in plan and in elevation. So how to avoid this eccentricity in buildings in plan? The thing is, I try to modify all the stiffnesses in both X and Y direction, and so balance them such that the stiffness center is very close to the mass center, or also called rigidity center, very, very close to the mass center. By making this eccentricity very small, I see that the torsion component is very small in the modes. The IS 1893 specifies that in the first three modes, we should not have any torsional mode at all predominant. So if it is, I'll go to the table here. I can show you the table. This is one more such building. This is one more such building, the three-dimensional effect. Okay, three-dimensional view. So again, it's a highly eccentric building in plan. In all such buildings, I can show you. These are floating columns. Again, soft story is one more. We should not have soft stories below. So any story below should have a stiffness not less than 75% of the story above. Stories above can be softer than the stories below, not the other way. There's one more, because soft stories are not good. See here, here UX is 0.367 in the first mode, UY is 0.19, while RZ is a torsional component is 0.442. It's not good. 0.442 is much more than 0.367, 0.19. So this is a highly torsionally irregular building. For example, here UY is 0.809. It's okay. Second mode is okay, but this is quite small. But this is very, very small. Okay, this second mode translation is good, is tolerable. Then third mode is 0.582, and this is smaller than that. So third mode is okay, second mode is okay. The first mode itself is not good enough, because I want to reduce this 0.442 also to be less than 0.367. So this kind of modification is possible when you keep on adjusting the stiffness of the various columns, such that the eccentricity becomes much smaller. So this is one which troubles us a lot. The building plan cannot be changed because of the architectural reasons, but we get results of this kind. For example, somewhere here in the 16th mode, we got a torsion component of 0.993. But here, I found out a method which I told Prasad, and it is yet to be confirmed by the IISc code people, that, generally we go up to certain modes, like maybe in this case, we went up to 18 modes, we get sufficient mass participation. 65% was, but not in first three modes. Supposing you accept that, within that, you find the torsional component 0.983 to be much far away in the 16th mode compared to the third mode. Therefore, I can say this is okay still. Although here it is not okay, here it is okay. So this kind of small, compromises, reconciliations, and modifications are required in order to satisfy both the architect and the IS 1893. See, these are the one. These are the modal participation mass ratios. They're very important here. Okay. Sum of all the masses in the x direction and the y direction, there should be a 0.6 here. It should be 0.65. It's not happening. So this is the one which worries us. 0.65 is 65%. It's only 60% here. So like this, there's so many tables that are in my book. Okay. Those interested can buy, they can refer to my book. Still it is yet to be released in the market here in India. It is released elsewhere, worldwide. Okay. By the CRC press. Okay. See here, this is again one more modal direction vectors. Here 0.98 in 0.989, 0.9, this is it. This looks to be okay. Okay. And these are quite small. But here again, you find torsional component larger. So my own modification makes it look okay, but actually it is not okay. So whether I accept my modification or you go by this is a question which is to be debated now. So this all I think I can show you. There's so many things like this. I can keep on going for even another several hours. I don't think you will be able to listen to me also with good attention, because it's time for you to have your lunch. Maybe I leave you here with any more questions you have. Okay. Thank you very much. Pardon me, sir? Pardon? Who is speaking? Yeah, tell me. Yeah, except from Etaps. Yeah, exactly as it is, which has been there implemented in design. Practical exam. Yeah. Thank you very much for your good patience and it is useful to you. Thank you. Right then. Fine, sir? Yeah. Yeah. We'll disconnect. Thank you, very much. Thank you, good person.